Okay, so we're very happy to have Ermek Nurkhaidarov from Penn State, Mont Alto, to talk about generic automorphisms. Go ahead, Ermek.
All right, thank you. So as my topic suggests, I will be talking about generic automorphisms. So in particular, I'll be talking about two types of generic automorphisms, so-called small index, which were introduced in Hodges, Hodkinson, Lascar-Shala 93 paper. And I will be talking about trust generics, which was introduced in the Trust 92 paper. And I will study a connection between these two types of generic automorphisms. And then we'll switch to models of Peano arithmetic. Throughout this talk, I will be assuming that we are working with countable models, and we will be considering automorphisms of such models. So when we're talking about automorphism group, we can consider it as a topological group by setting their stabilizer, pointwise stabilizer of finite subsets to be basic open subgroups. Throughout this talk, I will use notation G for automorphism group of M. And if A is subset of M, I will write G sub A for pointwise stabilizer. So first definition is definition of trust generic. So an automorphism F of M is called trust generic if its conjugacy class, set of all conjugate automorphisms, is commutative in automorphism group of M. And we will say M or automorphism group of M has trust generics if it has trust generics. Okay. Now we'll try to move on to the new definition of small index generic automorphism, which is a little bit more not as straightforward. So to go there, first I will introduce the definition of small index. So we'll say subgroup of G has small index if its index is less than 2 to omega and large otherwise. If we have element A in M, then pointwise stabilizer of element will always have a small index. It's kind of straightforward because we always have a projection between the set of right cosets and the set of all images of A under automorphisms from G. So from here we conclude that if GA and any open subgroup of G, if we have GA and any open subgroup of G, then we're going to have a small index in G. We will say that M has a small index property if I converse. That is, every subgroup is open if and only if it has a small index in G.
Hey, Luck, is it going?
Sorry? Okay. If G has a small index property, then we can recover topology of G from its abstract structure group. And for example, this can be used to reconstruct some information about the structure from its automorphism. Now, to define small index generics, we firstly define what is base. So base for M is a set of subsets of M, and they're going to satisfy two conditions. If A is in the base, then it stabilizes open. And the second one is basically saying that that base is open under automorphism. So if A belongs to base, then its image also in the base. Okay. Now, definition of a base automorphism. So if we have automorphism, when we're going to say it's a base automorphism for that particular base B, if the following holds, so if we start with any, so we start with any A in base, then set of all B's which are bigger than A are going to, and point-wise stabilizers, then they're going to be base of open neighborhood of 1 in G. So that's kind of implying that that we have a following situation. So we have A, and then we can extend it, and we can extend it and extend it. So eventually we're going to get toward the whole model. And that's going to be kind of on each step, we will be able to extend so that the G will be stabilizer of that set-wise stabilizer of that particular base set. And the second property is saying that if we have G, which is fixing a set-wise, and A is inside of another B, and we'll have, and if possibly we can extend G by HI, which is automorphism of B, then essentially that H is already our G. The difference might be only that it's is conjugated. That's part 2 of the definition. Here, second part. I'm going to give a minute or two to look at that definition. It's a bit technical. So from second part of the definition, it follows that if two base generic automorphisms are equal on a particular base set, then they are conjugate. Okay, we'll move on.
Can you go back just for a second? So in this definition, is n fixed?
In this definition, n is fixed. Yes, usually we will be talking about tuples of automorphisms.
So there is no condition about what happens when n increases?
No, there is no condition. Okay. So if we fix n, and we'll say that's a tuple of length n. But for small index generics, for to them to exist, we'll have to say that's for any n it will be exist.
All right.
So in this definition, it's n is fixed and nothing else is happening. We'll say it's tuple of length n. But in the definition, the next one will say that's for every n we're going to have a meter. If that makes sense. So now definition from the same paper, which is Hodgkinson Laskar 93. We say that model M has small index generic automorphism. If we have a base, and in this base for every n less than omega, for every standard n, a set of base automorphisms of G is commigral in Gn. Is that the one, Roman, you meant to ask?
Yes, yes.
May I ask a question also?
Of course.
As a topology, or is this the same word is used? Is there a topology behind this, or is this a different use of the word
So
base?
topology behind that?
Well, one talks about the base of a topology, so
Mhm.
that's not happening here.
It's
different
not
base.
happening here. It's happening behind the scene.
Yeah.
So basically, what is happening behind the scene is if we have small index generics, then the model is going to have a small index.
Right.
And actually, even though it's happening behind the scene, even in the definition of a base, if you look here in the very first step, we require that it has to be open right here. Yeah, so it's kind of happening, but on some level, but not maybe not in the definition of a base automorphism, but because we set up some restriction on a base, we'll have something going on.
Thank you.
Okay, so that's definition of small index generics automorphisms, and then the main theorem from that paper was that if a countable model has small index generics automorphisms, then M has the small index property. Okay.
Sorry, can you go back to the definition of a base automorphism?
Here?
Yeah. So, right. So it doesn't actually say anything about small index property in here. So
No, that doesn't.
Right. Okay. I just wanted to see if I missed that.
So, okay. So HLS paper proves that if M has small index generics, then M has the small index property. And then they constructed few examples. So they show existence of small index and therefore the small index property for the countable random graph and for omega stable omega critical structure. Laskar 93 paper is using small index generics to show that countably arithmetically saturated models of Peano arithmetic have a small index property. We'll talk about Laskar 93 paper like in a few minutes. First observation about the connection between small index and transgenerics automorphism is because they both are Komiker sets. Then if a model has both small index and transgenerics, then they should coincide. For example, we know existence of small index generics automorphisms for the random graph. And we know also that a random graph has the transgenerics. Therefore, for the random countable, for the countable random graph, small generics and transgenerics coincide. So a countable random graph have both small index and transgenerics, and they are coincide.
Ermek, just a historical question. So was this already noticed by Truss? Or this is because then there was something that Steve Warner did for the random graph. So is this something that Steve Warner did, or this is something that was known earlier?
I mean, the small index was proven, I believe, in that HHLS 93 paper for the random graph. We use the result for
Oh,
Khrushchev's.
I see. So Steve was doing some. Oh, so maybe this Steve did something about cofinarity.
Maybe
Oh, you using that. All right.
I'm
don't
not
quite
familiar
remember.
with that. I mean,
Yeah.
my impression was that was the first time small index property for the random graph was shown using a small index.
Right. It
generic.
was in the original paper, but then I just wondered the connection with trust generics, because the HHLS, they do not mention trust, do they?
They don't. I don't think
Right.
they don't.
Right. Oh, I see. Rehana has a comment about it. Right. So this was about cofinarity. So but he used this whole technology to do the uncountable cofinarity of the random graph. All right.
Okay. I guess so now we'll try to do a few examples to get an idea what is going on. So I'll do an example of a dense linear order with no endpoints. It is known that the dense linear order has generated automorphisms. That's in TRUS 81 and 92 papers. So lens linear order has small index property and has TRUS generics. We'll show that dense linear order has no small index generics. So I'll use Q for countable model dense linear order with no endpoints. So it's kind of nice structure. But first thing we notice that if we have a B is finite subset and A is outside of that B, then we can always find automorphism such that F will fix B pointwise, and it's going to move A to somewhere. So next lemma will show that if we have B in Q and pointwise stabilizer B is open, then B better be finite. It's kind of straightforward proof. If we assume it's B is not finite and it's infinite, because stabilizer of B is open, we can find finite A such that G is subgroup of G of B, and we can find B outside of A, but inside of B. So by previous lemma, we conclude that that element of B will be moved, and therefore F does not belong to G of B, but it belongs to G of A, which is contradiction. Okay. So from here, we get a corollary. So if B is a base for Q, and B is element of base, then B is a finite, because the first requirement for base was that stabilizers of its will be fine, will be opened. Now, second observation. Now, if B is in Q and B is a finite and Fn belongs to G, then if B fixes B set-wise, then actually fixing that finite set pointwise. And from here, we can obtain the property that Q dense linear order does not have small index generics automorphism. So it basically follows from that fact that which what we just mentioned, that the only possibility for a base is going to be consisting of finite sets, and as soon as we start the finite sets, then it will imply that it has to fix that finite sets, bigger and bigger finite sets, and eventually we're going to get only identity. So I think more or less formal proof is sketched here. So if I want to try to read it or move on and skip it, if it's obvious. Or you want to look at it? Do you want me to read it at the same time? I'm not completely sure.
Just give us a second to look at it.
Yeah.
I think it's
So, so basically, again, we start with our arbitrary base for Q and assume that we have some base generic. Then, because it's base generic, it should fix some A setwise. So we'll say f of A equals to A for some base set A. Then by definition of base, set H, which is a set of pointwise stabilizer of B, where B is in the base and B contains A, and f of B equals to B. That is supposed to be base of open neighborhoods, 1 in G. Now, because B belongs to the base and f of B equals to B, so we conclude that B is a finite and actually f has to fix it pointwise. So we redefine what H is. And again, now we conclude that for every C in Q, we can find B, which is a base set, such that G of C will be, so G of B will be subgroup of G of C. And from here, we will conclude that B is bigger than C, and F is their identity on B. And because B is getting bigger and bigger, we can pick it for any, so F is going to be identity on C. And we conclude that F is identity, and therefore we cannot have small index generics in so something like that. So if okay, I'll try to move on. So again, I'll remind you that truss result, that dense linear order has small index property and truss generics. Combining that with the lemma we just stated, we conclude that even though Q has the small index property and truss generics, Q does not have small index automorphisms. As we mentioned earlier, there are 4 possibilities for a countable model. To have both small index and truss generics, to have small index but not truss, to have truss but not small index, and to have neither a small index nor truss. So far, we constructed 2 examples. The first example was the random graph, which has both small index and truss generics. And the second we just constructed this a minute ago, which dense linear order. Dense linear order has truss generics, but does not have small index generics. Okay. Now we'll try to address the over 2 situation. So to address the over 2 cases, we consider a model which consists basically of 2 copies of dense linear order, so Q times 0, 1. Then we notice that automorphism of that model will either preserve each copy of Q or will switch with that, switch them. Therefore, such models, in particular Q times 0, 1, cannot have truss generics. By a similar argument we just did a few minutes ago, we can show that Q times 0, 1 cannot have small index generics. So That is an example of a model which is going to have neither trust nor small index genetics. Okay. And the last example is.
Ermek,
Yeah.
so what about the small index property?
I believe it does have small index because it's basically, you know, it's your regular dense linear order, right? It just, I believe it has small index property.
But I wonder how one would not, well, without SI generics. Oh.
Sorry?
So, all right.
Because it's essentially your Q, but you know, it's like kind of not double, but you can see what kind of.
So in other words, you would just conclude a small index property from the small index property for Q.
Yeah.
All right.
I believe that's how it is going to work. I'm assuming that should not be difficult to show, but if M has a small index property, then M times 0, 1 will have small index property. I think it should be true in general. And the last possibility, if we consider either random graph or omega stable, omega categorical structure, then M times 0, 1 has small index generics, but it does not have trust generics. So M cross 0, 1 has no trust. It's basically the same proof as we just did a second ago, we just mentioned for dense linear order. So basically the same thing. And to show that M cross 0, 1 has small index, essentially you have to go through the steps of a proof in the original HH similar to HHLS 93 paper. So it may be a few modifications. It's actually not too difficult. So let's this example. Okay. So we have all 4 possibilities, and they all do exist in the somehow all possible. Right. Now I will switch to models of Peano arithmetic, and we'll consider what is happening or what is known about generics in models of Peano arithmetic. So we'll assume that we are familiar with basic properties of arithmetic. In particular, I'm going to be working with recursively saturated models. So M is called recursively saturated if it realizes all recursive types. And models called arithmetically saturated if it realizes every arithmetic type over type of A, where A is an M. And when M is recursively saturated but not arithmetically saturated, will such M just recursively saturated. I think that was definition which came from somebody from that seminar suggested to call it just recursively saturated. I recall it correctly. When we're working with model of Peano arithmetic, if we have an element in M, when it's got a sequence A0, A1, and so on. For example, we can define AI to be the greatest Y such that EY, Y divides A, where PI is I. Just regular coding inside of models of Peano arithmetic. We say the standard cut is strong in model of arithmetic if for every A, there is C bigger than omega such that for every I, standard I, AI is standard if and only if AI less than C. And then Kirby in 84 paper showed that if M is a countable recursively saturated model of Peano arithmetic, then the following are equivalent. M is arithmetically saturated if and only if standard cut is strong.
A small comment, Ermek.
Yes.
Laurie couldn't have proved that. Laurie have. Did you? No, because I don't think arithmetically saturated models existed then. So, but maybe you wanted to comment on this anyway.
Funnily enough, I was just trying to remember, did I really prove that? So I'm rather glad I...
Laurie, you did, but you didn't know.
It was implicit, even earlier than 84 in my work with Paris, I would say. But yeah.
Yeah, I mean, I agree that definition of arithmetically saturated was not existing in 84. But as Lawrence was saying, it's implicitly was proved in that paper, or maybe earlier papers. So I still believe that was somehow, even in some of your papers, Roman and Jim, to Kirby.
I think this is also implicit in Kirby's thesis, right?
But I don't, well, maybe Laurie remembers. Better was in Laurie's thesis, but I do look at it now and then. But I don't think saturation played a big role. And I don't, one needs this sort of standard system saturation that was part of the folklore anyway. But I don't know if it sort of, if it explicitly was there in the thesis. Was it, Laurie?
Not at all, no. But arithmetical comprehension wasn't even really there. So, but yeah, it's implicit. It's implicit.
It's implicit. Everything's there already.
Well, I guess anyhow. Laskar in 94 paper applied that technique from Rogers, Hodkinson, Laskar, Shilla paper to show a small index property for countable arithmetically saturated model of Peano. So to apply that paper, I guess it's a regular comment. He constructed a base. So let's come up with definition. If A is subset of M, we say A is small if A is ordered by an element. And the base which Laskar is using is the collection of all small elementary submodels of M. So I could, on this talk I called A of M. So A of M is collection of all small elementary submodels of M. Then clearly then A of M is a base because it's, every subset is open and automorphism image is going to be still in will be still small elementary submodel. There is one twist on that definition. So we needed one more restriction on automorphisms. So if M0 is a small elementary submodel of M, and alpha is automorphism of M0, we say alpha is extensionally closed if alpha can be extended to an automorphism of M. And second, for all formulas phi of x, if parameters in M0, if there exists a beta, which is automorphism of M, extending alpha, and B in M such that M proves phi of B, beta of B, then it's already happening with alpha in some element C. Then there exists C in M0 such that M proves phi of C and alpha of C. Okay, so that's definition of x extensionally closed. So then Laskar defines the definition of base automorphism, which is essentially the one which we mentioned earlier, with extra condition that with an extra condition to be extensionally closed. So that's exactly the same definition it was originally, with extra condition that to be existentially closed, but otherwise it's one-to-one as before. I stated for just one automorphism, but it can be restated for a couple of automorphisms. That's only added extra requirement. And then in 94 paper, Laskar proved that for countable arithmetically saturated models, the set of base automorphism for this particular base is comigrant closed under conjugation. And if AF is a small index automorphism, then for each finite AM in M, there exists small elementary submodel M0 such that A in M0 and M0 equals F fixes M0 setwise, and F bounded to M0 is existentially closed. And if F and G in automorphism of M are small index automorphism, such that for small M0, they fix in M0 setwise, and if they are equal on M0, then they are n extensionally closed, then F and G are conjugate. So it's basically the same properties as we mentioned earlier. The only difference is that we have like extra condition that that existentially closed, no automorphisms. Then standard definition of initial interval. If F is automorphism M, then I fix is the largest initial segment pointwise fixed by F. So we'll need the following lemma proved by Kotlarski 84, Smarinsky 82, and Pensovska, published. So if M is countably recursively saturated model of A, and A, B, and C in M, suppose that for all n and omega and all formals phi of x, y, M proves that for all x less than 2 to an phi of x, b, even only phi of x, c, then we can find automorphism such that f of b equal to c and a belongs to I fix of x. And here that's 2 to the an and iterated exponential growth. So I'm defining all this definition. My goal is kind of to introduce that Shmurlov-5 theorem, which he said that small index and transgenerics do exist for their arithmetically saturated model of true arithmetic. So that's our goal. just for now. So we define the gap. So if M belongs to M, when we define the gap, so we say that's a set of all elements B, such that we can go beyond A using B, but also above B using A. So A and B basically live on the same floor. The following lemma is not difficult to show. So if M is countably recursively saturated model, A and B and M, such that type of A equals type of B, then we can find C and M such that type of C is indiscernible and type of C, tuple type of CA and type of CB the same, and gap of C is bigger than gap of B from A. And a standard definition of indiscernible and indiscernible or minimal type. Okay. So we define true arithmetic to be the complete theory of standard model of Peano arithmetic. Now, if M is a countable arithmetically saturated model of true arithmetic, if we have A, B, C, and D in M such that type of A equals type of B and type of C equals type of D, when we can find C prime, D prime, and M such that type of A, C prime, and type of B, D prime will be the same. And the proof, a bit technical here, sketch the proof on like a couple of pages. I'm not sure how much we want to go into it. I guess at least let's try to read what's here. So sketch of proof. So we will fix some B prime, which so its gap is bigger than gap of A and B. Because M is true model of true arithmetic, and we have arithmetical saturation, we can find F automorphism of M and C prime, D prime, and M such that A, B, B prime belongs to the I fix of F, and F of C prime equals D prime, and C type of C prime, D prime equals type of CD. By the previous lemma, we can find, by applying the previous lemma a couple of times, we can find C2 and C3, and H of automorphism of M such that H of C2 equals to C2, H of C3 equals to 3, and H of A equals to B. Assuming that gap of C2 is bigger than gap of C3 and gap of B prime. And type of C2 is same as type of C3 and is indiscernible.
Yeah. I do not quite follow, but one small comment that the type is not quite recursive because of the third line, that it includes the types of CD. So that is a non-recursive. So if you have arithmetic saturation, it's an arithmetic type in the type of CD, but.
Okay, yeah. Yeah, it should be. And because we are working with arithmetically saturated model, I guess that's still fine. So we'll show that this type is consistent. So we show that this type is consistent by doing the regular step thing, just using the list C prime, D prime, which satisfy particular properties. And I guess we'll go on from there. And again, I'm not sure if you want me to read it or just look at it, glance at it, or skip it for now.
I think it's fine. You can continue.
Okay, yeah. So, and then we can move it. I mean, anyhow, then
So maybe one thing you could show us, where is it essential that this is a model of TA?
Because we're working with true, yes. So we don't want to interfere with smallest interstices, because
Right. So in other words, you don't want to do these things among the definable elements.
exactly. So I want to have my definable elements to be only in the standard cut. I
Right.
don't want to go there. So I want to have like that clear distinction. So that's not the original proof of Jim. So Jim proved it differently. I will outline how Jim proved it. Jim used some combinatorial results.
Mm-hmm.
I tried to improve on that statement of Jim, and I was working on it, and I will start working. I definitely need to have recursive saturation. Then I figure out I actually need arithmetical saturation. And then I struggled with that particular lemma, because if I have non-standard definable elements, they will interfere with my definition of somewhere here. I don't remember exactly. Yeah, they will interfere with definitions. So I end up with exactly the same result as Jim eventually. So yeah, but yeah. So basically, I want to have a clear cut between definable elements, and in order to have a clear cut, that's why we will need to have a true arithmetic. So Schmurl's Jim's O5 theorem says that if M is countably arithmetically saturated model of true arithmetic, and M has both small index and transgenerics. So if we know the previous lemma, then it's not too difficult to outline how the proof might go. So what we do is we show that two small index generics are conjugate. So we start with two small index generics, and if we pick A and C, so that A and C are coding small submodels, correspondingly A and C, and F and G are existentially close on correspondingly on A and C. Assume that F of A equals B and G of C equals to D. Then there exists a generic, a small index generic H, such that H of A equals to B and H of C prime equals to D prime, and type of CD equals to type of C prime D prime. That follows from the previous lemma. Then F and H are conjugate, since they are equal and existentially close to an A. Then we pick alpha automorphism of M, such that alpha of C equals C prime, alpha of T equals T prime. Then conjugation of G by alpha is a small index generic. And alpha G, alpha inverse of C prime equals D prime. Therefore, alpha G, alpha inverse, and H are conjugate. And so from here, we conclude that F and G are conjugate. So any two small index generics are conjugate, and we conclude that they are also trust generics. Okay. So that's this proof. And original James proof was a bit different. So it used some combinatorial results. So I guess I'll mention that too. So digraph T is a pair of B and E, where E is subset of E squared and X is not H whenever X is a vertex. The direct product T1 and T2 of two graphs is digraph V1 cross V2E, where the following happens. Function alpha is a C coloring if it's from V to C, and if alpha of X is not equal to alpha of Y whenever they share the same H. Chromatic number is the least cardinal for which there is a K coloring. So that's this. Then HK lambda statement. If we have two digraphs T1 and T2, such that chromatic number of D1 and chromatic number of D2 is at least K, then chromatic number of D1 cross D2 will be at least lambda. There is that known result from combinatorics, 85 statement that H of omega Aleph0, and Jim was using that statement to prove a result we already mentioned, that if M is countably arithmetically saturated model of true arithmetic, then M has both small index and trust index. And again, in that Schmerl 5 paper, it is shown that existence of trust generics is very closely tied to the Hedit-Nemis conjecture, known open conjecture in the chromatic field of graphs. So if M is not model of true arithmetic, countable arithmetic saturated, then the following equivalent, M has trust generics, and there is N less than omega such that M proves H of N over 4.
Oh, I have a question or maybe a small comment here, because it's been a long time since these things were, what's 17 years ago. But wasn't this equivalence originally, so trust generics are those that have conjugacy classes, but wasn't the theorem about those automorphisms that have dense conjugacy classes? And is that equivalent to trust? Or is it equivalent to having trust? I guess it is from the theorem, but I thought the original theorem was that this equivalence was the equivalence between having automorphism with dense conjugacy classes and the Head-Nimi conjecture.
Oh, maybe Jim can better answer on that question. I don't know what was the original one.
Yeah, actually, I don't remember exactly what it was.
But it's
But I do know that Head-Nimi's conjecture has been disproved.
Oh, when?
Oh,
But
Oh, I see.
but
That's
it
right.
doesn't it doesn't affect my theorem at all.
oh, so it's disproved in general.
I'm sorry?
So it's disproved in general, but it might be still true for particular cases.
The equivalence that I showed was to sort of a weaker form of Head-Nimi's conjecture, which is still open.
Mm-hmm. But I do remember that the I don't know, in the original paper, perhaps from the existence of dense automorphism with dense conjugacy class plus a little bit more, you prove the existence of trust. So these things are really equivalent. So anyway, so this was a slightly stronger theorem, but equivalent.
Yeah, it could be. I don't remember.
I think I remember, but I may be misremembering. It's easy to check, though.
Yeah,
it's in the book.
Could be.
So that was the last statement I wanted to mention here. So that's basically what is known about generic automorphism. So I worked on that like with Jim like 20 years ago. I believe I did something like oral presentation on the Laskar article, maybe like again in 2002 or something. And yeah, not much has happened after. So we don't know if we have a small index or trust generics for just recursively saturated models of Peano arithmetic, or whenever we have trust generics for arithmetically saturated models, which are not models of true arithmetic. So that's, I guess, the end of my formal part of presentation.
Okay, great. So let's all thank Ermek. You can either unmute or put in yours.
Thanks, Ermek.
Thank you, Ermek.
Yeah.
And let's, so there were plenty of questions during the presentation, but if, please feel free to unmute or raise your hand if you have a question now. In that case, I will stop the recording here.